Hello everybody, this is Dr. Thunder. Today, I would like to show you how to use integral method to prove Newton's shell theorem. Newton's shell theorem says that if the body is a spherically symmetric shell, like the hollow ball here, then no net gravitational force is exerted by the shell on any object inside. For example, this object M is inside this hollow ball, regardless of the object's location within the shell. So if this object is anywhere inside this hollow ball, its gravitational force is zero. This is part of Newton's shell theorem. Today, I would like to use the integral method to prove it. So let's draw the figures here. So here is M inside this the hollow ball, or it's a spherically symmetric shell. So now we take a circle here. So the circle will have a form angle of theta with the vertical axis. Now we can draw the cross-section of the ball here. So this is y-axis, and then this is the small object inside the hollow ball with a distance a from the top, and then this is the strip we take. So at theta angle here, so we only take a very narrow strip, so the width will be r d theta, and then the whole strip is like that. If you look at in 3D, in this 2D image, we can only see this part. So the this circle circumference is 2 pi r. This is r sine theta. So let's look at the expression here. So dF will be g, gravitational constant. M is the mass of the small object inside the hollow ball, and then r d theta is the width of this ring in origin color, and then 2 pi r sine theta. R sine theta is radius. 2 pi r sine theta will be the circumference of this circle. Rho is the density of the mass of this hollow ball, and then the distance from this to the small object M, we define the distance as L. So we simplify this to be that. Now we know that L will be, this is a right triangle. So this one is L sine theta. So then we have r squared sine squared theta. And then this part, remember from here to here is r minus a, right? And then from here to here is r cosine theta. So this the length from here to here will be r minus a minus r cosine theta. So we can get the expression for L. And then only the force along the y direction will count. The force component that is in this surface will cancel each other because due to its symmetry. So we only calculate the dFy. So dFy will equal to dF, and then this length, which is r minus a minus r cosine theta over L. So we we plug df expression here and clean up, so we get this expression. So this dfy is for the integration below this particle m, below, for example, like here. For df above this object m, for example, if we calculate the integral for the dfy here, then the sign will be different. But remember, if the integral happen here, then effective df is pointing downward. So 2 minus 1 will become 1. For the dfy below m, for example, here, the df is positive, dfy is positive. So in the end, the expression for dfy is the same for all cases, whether it's above this particle or below this particle. So we have this dfy expression here. Now we do the integration. Fy is integral of dfy from theta, when theta is from theta equal to 0 to theta equal to 180 degrees or pi. So we plug this expression here, and then we also plug the expression for L here. Now we do some change. We assume Z is equal to R cosine theta. Remember, D cosine theta is minus sine theta. So then we change into this expression. Remember, R cosine theta is Z. So, and then these two limits change from 0 to pi to R to minus R. Then we do the integration, and finally we get this. When we come to here, we assume this part is C, and then we assume this part is D. So the integration of this part becomes like that. Now if we can check, use Google to check the answer, we get this expression. Remember, C is here, D is here, and then C1 is a constant. Then we calculate, we plug R to this expression, and then we also plug minus R to the expression. In the end, this integral becomes 0. So which means Fy is 0. That means the force that this particle feels is 0. So this is again, this is Newton's shear theorem. If the body is a spherically symmetric shell, no net gravitational force is exerted by the shell on any object inside, regardless of the object's location within the shell. So regardless of the location of this object inside this hollow ball. Remember, when we pick A here, it's random. Eventually, regardless of the value of A, Fy is 0. So we this way we proved part of Newton's shear theorem. Thank you for viewing. If you like my video, please comment, like, and subscribe.